Couple comments real quick about last lecture that I want to make before we move forward today about talking about errors and stability of schemes. When you're in MATLAB, and I'll give demonstrations of this probably even either next lecture or the one after about how to use some of the ODE solvers. One of the things you want to think about doing is, well, I want to solve this differential equations. And what I introduced last time were these basically iteration schemes for solving differential equations. And let me just tell you a little bit about some of the power you have available to you in MATLAB. So you have things like, this is probably the most common, ODE 4-5. Okay, so let me actually write down a list of what these are, and then you might say, well, what do these numbers all mean? And today we will find out what these numbers mean. So in some sense, this is okay. So for instance, here is different differential equation solvers you could use. ODE 4-5. This is fourth order Runge-Kutta. Fourth order, 4, 4, 4. There's a 4. So somehow maybe that 4 is related to fourth order Runge-Kutta. So in fact it is. We'll talk about what these two numbers mean. What's the 5 doing there? Because you know Jordan was 45 when he came back to the Washington Bullets. What was that team? Yeah. Wizards, yeah. They changed their names from Bullets to Wizards. Anyway, he was number 45. Now you might think he's not as, he wasn't as good when he was 40, because there's OD 23. You might think, oh, that Michael Jordan wrote that. Turns out he didn't. But we'll talk about it. But see, you see the Michael Jordan numbers right there, and you might think, well, there's something here. I know. It's kind of like magical. I don't know about if there's anybody in the NBA with a number 113. I think they don't allow it. And then OD 15S. Okay. So what these are, fourth order Runge-Kutta, second order Runge-Kutta. This is a predictor-corrector method. What does the 113 mean? We'll think about that later. And OD 15S. And the S stands for stiff. So there are problems that have what is called stiffness in them, and these are based upon gear methods to solve stiff problems. So we'll talk more about these later. But you see, you have access to quite a variety of stepping schemes for solving these equations. So what we're going to attempt to address today is a key issue that all of these have to deal with, which is accuracy and stability of the scheme. Remember, they're just iterations. They're just simply you set something up and you just iterate. For loop to step forward into the future, solve your equation. So first of all, you want to make sure that that stepping routine is stable. Second, you would like to know at the end of the day, when you produce a solution, how accurate is it? Right? This is pretty important, that you understand how good your solution is. All right? So we're going to talk about these issues in the context of ODEs. And so we're going to do sort of an error analysis. Okay? So first of all, let me start off with this function here. And by the way, I'm trying to solve the following differential equation here. And let's just consider this for a moment, independent of this. Well, here, we're going to do something to this. We're going to Taylor expand it. Now, let me tell you, Taylor expansions, now you may have thought they were worthless, and you're like, why do we do these Taylor expander? You're going to Taylor expand everything all day, all night in this class. All numerical schemes are just Taylor expanding everything in sight. Okay? Just want to throw that out there so you're comfortable with Taylor expansion. It's like the most useful thing you ever learned in calculus. And you didn't even know it. But here it is. It's all we're going to do, because we're not going to ever do calculus. The whole point of computing is to undo calculus in some way, because you don't know how to divide by 0. So you paid a lot of money for that calculus course, probably. No refunds now, probably. Okay. But Taylor expansion was one thing that came out of that, and so you can always say, at least I got one thing to still use. And here it is. If you Taylor expand this thing, right, you say, I'm going to Taylor expand around y of t, and you get stuff like this. You can say, I'll just keep Taylor expanding. Well, That one doesn't have anything divided yet by it. Delta t, and then you have dy dt plus delta t squared over 2, second derivative. Now there's an option for you here, if you remember your Taylor expansions, is that you could just keep expanding forever. Or you can truncate. And you can say, I will truncate right here. I'm going to evaluate that thing at some c. I don't know where that c is, but what I do know is that the c lives somewhere between t and t plus delta t. This is exact. Okay? I haven't made any approximations. The only problem with it is I don't know what c is. Fair enough. Still, I have an exact formula. No approximations so far. Now, here's the thing to notice. All we did was Taylor expand. Nothing fancy. Now we're going to relate it to our differential equation. Our differential equation is right there. And all the differential equation tells us is what the derivative is. dy dt is f. And you see right there, there's a dy dt. Let's put f in there. So you can see that what I have then right? And let me put this here. I'll explain what this means in a minute. My solution in the future is what it is right now, plus a little bit of something. I just got back the Euler formula we did in class yesterday, right? From Taylor expanding. So this is just an alternative way for you to do it. Last time I just used the definition of derivative, and I got the Euler formula. Here, I'm Taylor expanding, using that for put it there. And here's the important thing we're going to talk about, though, today, because last time when I did it, I just kind of did it, and I didn't tell you how much error I made in doing that. But now I can tell you, check this term out. Order delta t squared. So that's big O. Big O is order. It's the order parameter, order symbol. What it just tells you is, how big is this term? Well, it scales like delta t squared. That's how big it is. So if delta t is small, let's say delta t is 10 to the minus 2, then if I truncate, because this, you remember my Euler formula just used this part here, right? So I'm going to throw that away. But what am I throwing away? I'm throwing away something that's delta t squared. So if my delta t is 10 to the minus 2, I threw something away that was 10 to the minus 4. Okay? So it's kind of very intuitive to think about, okay, I know how much I threw away, so that's my error.